Okay, so let's go ahead and take a look at this next objective. So we're going to start by looking at just some sequences, just to kind of, I know we've done some series stuff and some sequence stuff in a previous class, but we do want to just kind of refresh our memory about, what a sequence and a series really is. So when we look at a sequence is just a list of numbers, usually based upon some sort of like rule or equation, and a series is something that where you take an equation, you plug numbers in, and then you add everything together. We're going to spend I would say almost 100% of this unit talking about series, not sequences. But just to give you an idea about sequences, just to kind of get our feet wet, if I list the first 5 terms of this particular sequence here, what I want to do is I want to take my n is equal to 1, and I want to plug it in, and then evaluate. So I get 2. 2 squared plus 1 gives me 5. 3 squared plus 1 gives me 10. 4 squared plus 1 gives me 17, and 5 squared plus 1 gives me 26. And so my terms of my sequence would be 2, 5, 10, 17, 26, and I could keep going on and on and on. And if I look at this 6 terms of the sequence, what you notice is that this n minus 1 in the exponent and my negative 1 in the front. What that actually does is it alternates my series. So what you notice is positive, negative, positive, negative, positive, negative. And so my first 6 terms of my sequence are down here. And I did the exact same thing to get them. I plugged in n equals 1 here for both of my n's, plugged in 2 in for my n's, plugged in 3 for my n's, 4, 5, and 6. Okay? So now let's look at a series, what we call a finite series. A finite series means that I have some sort of end up here. And so what I'm looking at with a series is that I'm going to start at n equals 1, and I'm going to go all the way to n equals 4. So I'm going to plug in 1 first in for my n, then I'm going to plug in 2, then I'm going to plug in the 3, then I'm going to plug in 4. Then I'm going to stop. Okay, and then what I want to do, because this is a series, I want to add all of these terms together. So my common denominator between all 4 of these denominators here is 12. So 12 over 12, 6 over 12, 4 over 12, 3 over 12. I add all my numerators together, I get 25 over 12. So this sum of this series is equal to 25 over 12. Okay. Now, we're going to look at what's called a Taylor polynomial. And a Taylor polynomial's goal, in a way, is to take any series, so any infinite series that you can create, and turn it into a polynomial. So what we have is e to the x, and we have sine of x, and we have cosine of x. And what I can do is if I do enough terms creating my Taylor polynomial, I can get a polynomial that looks almost exactly like the cosine curve. So if I look at cosine, just for an example, just look at cosine alone. You know what the graph of cosine looks like. It kind of looks something like this. Now, if I create in the dark line will be my actual cosine curve. In the dotted line will be my Taylor polynomial. So my polynomial that I can create, if I create it of a second order, and we'll talk about how you create a second order, how you create a third order in just a second. But if I create a polynomial, my polynomial looks really good, very, very close to x equals 0. Then it kind of, then the polynomial kind of pulls away from my cosine curve, pulls away here on my cosine curve. So it doesn't look as very good, not as accurate. If I do a fourth order Taylor polynomial, I get further out where my polynomial is almost exactly like my cosine curve. So what do you think with a sixth order, even better. So the more orders you can do, the higher the degree of the polynomial, the better the approximation to the exact curve. Okay, so there's two ways of generating a Taylor polynomial. And I don't know how good you are with memorizing. I'm not very good. So what I would do is I would only memorize this one. Okay. Taylor series generated by f at x equals a. If my a happens to be equal to 0, we don't call it a Taylor series, we call it a Maclaurin series. If we center it at any other value other than 0, then it is called a Taylor series, okay? And the Taylor series is created by taking your function, there's a step-by-step, taking your function or equation, and then you need to take the derivative. And the formula for generating the polynomial is the original function, x minus a to the 0 power over 0 factorial. That exclamation point is what we call factorial. In case you don't remember what a factorial is, if I have 4 factorial, that means that I take 4 times 3 times 2 times 1. So 4 times 3 is 12, times 2 is 24, times 1 is still 24. So 4 factorial is 24. Factorial is a number of ways I can choose an object. So if I have 4 different objects, then when I first try to choose one object, I have 4 options. And then I have 3 options. And then I have 2 options. And then I have 1 option. Well, what do you think 0 factorial is? How many different ways do you have to choose no objects? Well, if you have no objects, there's only one way to choose no objects, so 0 factorial is 1, okay? In case you don't remember factorial. So now, why do we do this? Well, we generate polynomials like this because we can, for fun. But we also do it because sometimes we need approximations. Now, obviously, if you had the cosine graph, you're going to use the exact value of cosine. You know, you're not really like, you know, going to use an approximation for something that you can find the exact value for. But sometimes you only have values for like position, velocity, and acceleration at a specific time value. And you want to know how to construct a polynomial that could tell you what could happen at a different time value that's close to the actual values that you actually have. So sometimes, I would say the majority of the time, like if I were to use this in like the real world, I would do this when I only had values of position, velocity, and acceleration. You know, you don't really do this if you have the actual equation. You normally only do this if you have values of the derivative. So there's other series that you can do called Maclaurin series, where you're centered at 0. And what I mean by centered at 0 is I just have e to the x. Technically, this is e to the x minus 0, but we only write it as e to the x. So we say that this is centered at 0 because I could have had e to the x minus 2, for example, and then that would have been centered at x equals 2. Okay, obviously if I had e to the x plus 1, this would be centered at x is equal to negative 1. Okay, but I can generate series for e to the x, sine of x, cosine of x, ln of x. Maybe I should use a highlighter. Sine of x, cosine of x, ln of 1 plus x, and tangent inverse of x. these are ones that, okay, so if I were to answer these questions on a multiple choice test will ask you to create the Maclaurin series for something like cosine of x minus 4. And if you had this whole polynomial memorized, then in theory, you could generate that polynomial very, very fast. So you could, if you had, that particular polynomial memorized. At the end of the day, it's not as easy to memorize all of these to answer a handful of multiple choice questions. Me personally, if I was, 24 hours before the AP test, I probably would not spend my time memorizing these, because I can create all of these by having just this polynomial idea memorized. And so in the end, I would spend more time probably memorizing, derivatives and antiderivatives of all my trig and inverse trig functions than I would memorizing all my Maclaurin series. But that's just me personally, because I can generate all of these series. I just can't generate them in a fast way. But there are ways to, do the first couple of terms of the series and then start weeding out the ones that are in the multiple choice. At the end of the day, you're probably not starting off your AP test with all of your series and sequence questions answering the first time around. You're probably skipping them, and you're probably coming back to them and answering all of the Calc AB questions on the multiple choice test. So at the end of the day, when you're looking at what are you going to do 24 hours before the test, I don't know if I would memorize your Maclaurin series or not. Completely up to you. So if I were to ask you how to create a second order Taylor polynomial centered at x equals 0, okay, for cosine of x, I need values. I need f of 0, f prime of 0, and f double prime of 0. Okay, so order and degree. Order tells you the number of derivatives. Degree tells you the largest exponent of x in the exponent. So the degree of a polynomial is the one that has the highest exponent of x. That exponent is called the degree of the polynomial. Okay, so second order, I need f of 0. So cosine of 0 is 1. And then I need the derivative at 0. Well, if I need the derivative at 0, then I also need the derivative. So this is negative sine of x. So negative sine of 0 is 0. F double prime is negative cosine of x. So negative cosine of 0 is negative 1. So I write my polynomial. F of 0, x minus 0 to the 0 exponent over 0 factorial, plus f prime of 0, x minus 0 to the first power over 1 factorial, plus f double prime of 0, x minus 0 to the second power over 2 factorial. So what does that give me? 1, because x to the 0 power is just 1. And then plus nothing, 0, because f prime of 0 here is 0. And then plus my negative 1 over 2 factorial, which is just 2, and then x squared. So my polynomial is 1 minus 1/2 x squared. Okay. And then my fourth order Taylor polynomial means I need 4 derivatives. So I already have 1 and 0 and negative 1. So triple prime is sine of x, and then that's 0. And then fourth prime is cosine of x, which is 1. So now I have 1 plus 0. Maybe I should write it out for you. So 1 x to the 0 power over 0 factorial plus 0 x to the first power over 1 factorial plus negative 1, x squared over 2 factorial, plus 0, x cubed over 3 factorial, plus 1, x to the 4th over 4 factorial. So I get 1 minus 1/2 x squared plus 1 over 24 x to the 4th. Okay. That polynomial can be used to approximate the value of cosine very, very close to x is equal to 0. And if you use this polynomial, similar to linearization, if you use your polynomial to approximate something very, very close to 0, like x is equal to 0.1, then if I plugged in 0.1 in for all of my x's, I would get very, very close to what the cosine of 0.1 is equal to. So the idea is for approximations. Okay. And what you notice is that, like, around cosine, around 0, it's very, very good approximation. Probably a little bit further out for a 4th order. Obviously, when I was just talking about this earlier, a 6th order, an 8th order, a 10th order. And I am using even numbers because all the odd ones give you 0. Okay? So if I wanted to use the memorized chart, this is what I'm talking about, is your multiple choice test would say, find the Maclaurin series for this equation. And what you have is you have that Maclaurin series that was 1 over 1 plus x. And that series is 1 minus x plus x squared minus so on and so forth. This is a memorized series back on that big page. So if I notice the comparison or notice the similarities, instead of x here, I have 2x here. So that means that I could take all of my x's that are here and replace them by 2x and get my polynomial. Okay, we can ignore this convergence part for a second because we'll talk about convergence later. But at the end of the day, that would be the benefit to having your Maclaurin series memorized. Otherwise, what you would have to do is you'd have to take your 1 over 1 plus 2x. I would have to find f of 0, f prime of 0, f double prime of 0, so on and so forth to create my polynomial. Okay, so that means I would have to take this and plug in 0 for x. Then I would have to take this derivative and plug in 0. Then I'd have to take the second derivative and plug in 0. So it is a little bit faster, or a lot faster, to be able to have that table memorized. But you're going to have to generate these polynomials on the free response test more so than multiple choice. So you're only going to get probably a handful of questions on series and sequences on the multiple choice test. Okay, so if I wanted to do the 3rd degree Taylor polynomial, degree means the number of derivatives that it takes. In this case, it will be equal, but the 3rd derivative, or the 3rd degree in this case, means 3 derivatives because the degree and the derivatives match. Okay. So f of 0, 0. And I'll show you an example. You'll see some in the review as well where it doesn't work out, where the degree and the order and the number of derivatives don't match. Okay. So the derivative of tangent secant squared, f prime of 0 is equal to 1. F double prime of 0 is a chain rule, so 2 secant x, tangent x. And then f double prime of 0 is 0 because the tangent of 0 is 0. F triple prime of x, we should do that first, will be, this is the same thing as 2 secant squared of x, tangent of x, so I need to use the product rule. So I get 2 secant squared of x because of the derivative of tangent, and then plus tangent of x, and then 4 secant squared sorry, not secant squared, 4 secant x, tangent of x. And so when I plug in 0, I get 2. So my polynomial, denoted as p with a little 3 in the subscript of x, is 0 over 0 factorial x to the 0 power plus 1 over 1 factorial x to the first power plus 0 over 2 factorial x to the second power plus 2 over 3 factorial x cubed. So I get my P3 of x to be x plus 1/3 x cubed. Okay? Last one, I only gave you derivatives, and I already wrote it out for you. But if I'm only giving you derivatives and I want the third degree Taylor polynomial, means that I have to go all the way to an x cubed. So I need g of 0. G of 0 is -4. So that goes over 0 factorial x to the 0 power. 2 goes over 1 factorial x to the first power. 6 goes over 2 factorial, and 8 goes over 3 factorial. So this is my polynomial. It says to then use it to approximate g of 0.5, which is really, really close to 0. So we say that g of 0.5 is approximately p of 0.5. And so then I plug in 0.5 in for all of my x's. And when I plug in 0.5 for all of my x's and I evaluate, I would get some sort of decimal. You're going to have to probably leave this as a improper fraction because I'm not letting you guys use a calculator in this unit, and your AP test, this will show up on the free response on the non-calculator portion. Okay? And that is it for this lesson.